So this is the fifth video we've made, and this is starting with the second page, number 27. As you could see, ladies and gentlemen, this is an exponential function. I don't know if you guys remember that, but it has the power of x. And exponential functions, they're either exponential growth functions or exponential decay functions. So, is this an exponential growth or decay? What tells you if it's growth or decay?
Negative or positive?
No. You guys are confusing the parabolas. This is not a parabola, guys. This is not an x squared. This is not a quadratic trinomial that has a power of 2. This is a power of x. This is an exponential growth or decay. So this is way back at the beginning. Now we're talking early January here. So you might have forgotten. This is your base. Remember your base? And if your base is greater than 1, then from left to right it will grow. If your base is less than 1, then from left to right it's going to decay to a certain value. Do you guys remember that?
Oh, it's lower than 1 then.
So it's less than 1, so it's a decay function. So from left to right, it's going to decay to a certain value. Now, most of the time, we have either a like -3 out here or a +2 out there. Right here, it doesn't exist, right? So if we did have a +3 or a -3 out there, we would ignore it and graph the parent graph. This is the parent graph, ignoring the plus whatever number you have out here. But in this case, we don't even have a number, so the parent graph is our final graph. So how would we graph this thing? Well, it's as easy as making an XY table. Let's all do that right next to this graph. Put an XY table, and we want to plug in some easy inputs. What's the easiest number to plug in? 0. If you plug in 0, what's your output going to be? Now remember, it's 1/3 to the 0 power. Anything to the 0 power equals 1. Anything to the 0 power equals 1.
Oh, yeah.
Okay, now, I hope we remember from back early January that the inputs we would use were consecutive integer inputs. They were in order, 1, 2, 3, -1, -2, -3. And we did them in order. That way we could use the growth factor or the decay factor, in this case it's a decay factor, to get from one output to the next output without doing that much math. Okay, so how do I get from this output of 1 to the next one? You simply make it decay by 1/3.
It's 1/3.
In other words, 1 times 1/3 is 1/3. And then to get to the next output, 1/3 decayed by 1/3, that's 1/3 times 1/3. What do we get? 1/9. And then from 1/9 to decay it by 1/3 again, 1/9 times 1/3 is what? 1/27. Now in reality, you don't need to be this specific. All you need to know is that 1/3 is less, I mean that's pretty small, but 1/9 is smaller.
It's getting closer to 0, but
Yeah,
whenever it touches
exactly. It infinitely approaches the value of 0, but it never actually touches. Now in the opposite direction, if we're multiplying by 1/3 here to get to here, and then multiply by 1/3 to get to 1/9, and then multiply by 1/3 to get to 1/27, going backwards is the reciprocal of multiplying by 1/3. It's actually multiplying by 3/1, right? So it's multiplying by 3. If I say 1/27 times 3, I will get 3/27, which reduces down to 1/9. And then times 3, I'll get 3/9, which reduces down to 1/3. And then times 3, I'll get 1. And then times 3, what do I get? 3. And then times 3, and times 3, 27. So we don't need all of these coordinates, but let's graph it. So let's graph the red coordinate right here, 0, 1. Let's go to 0 on the x, 1 on the y. There it is. Now this is not a parabola. This is a exponential decay function. Let's go to the next coordinate, 1 and 1/3. So what does that mean, 1 and 1/3? Check it out. Here's the origin. I'm going to go 1 on the x and 1/3 of the way up. 1/3 is not even halfway. It's about right there. It's almost halfway, but not quite. So let's put a dot at 1/3 of the way up right there. And let's go to the next coordinate. What is the next coordinate? It's 2 and 1/9. 1/9 is hardly anything. If you have 1/9 of a tank of gas, you better get to the gas station, right? So 2 on the x, 1/9. See, 1/9, it's so small that it kind of looks like it's touching, but we know it never actually touches. It just infinitely approaches. If you go to 3 and 1/27, you can't even really see the difference. It looks like it's a dot touching the line, and we know that how it continually goes. It infinitely approaches, but never actually touches. Okay, now let's go in the opposite direction. Let's go to the coordinate negative 1, positive 3. So you're going to go negative 1 on the x, positive 1, 2, 3 on the y, and put a dot right there. And then let's go to negative 2, 9. That's going to be off the graph, but I could show that. So negative 2, 1, 2, 9. Here's 8. One more would be 9. So let's go 1 unit off the graph, and it'll be right there. And then if we just connect these dots, we will have our perfect exponential decay function. Now, let me remind you this because, like I said, sometimes you will have a plus 3 out here or a minus 2 out here, and you would do the same exact thing that we just did, but if you had a minus 2 out here as a k value, you'd have to take each one of these coordinates and move it 2 down, move it 2 down, move it 2 down. This asymptote at y equals 0, you'd have to move that 2 down, and it would end up infinitely approaching this line right here. So if you had a minus 2, you'd have to move all the coordinates 2 down. If you had a minus 5, you'd have to move all the coordinates 5 down. Or if you had a plus 1, you'd have to move all the coordinates 1 up. I hope that makes sense. But right now, there is no number that you're adding or subtracting at the very end. So that is your answer. Let's just connect the dots. This is our exponential decay function, and it does infinitely approach, but never actually touches the x-axis, which is the line y equals 0. There's your exponential decay function. Okay. So knowing how this number out here will shift this graph up or down, right? And knowing that your a value is positive, it means that it's opening up. You'll be able to identify the correct answer on your multiple choice test. But this is how you do it. I hope we understand, and please watch this video over and over again if you need more help. Let's answer a couple more questions about this graph. What is the y-intercept of this graph? 0, 0, 1, right? It's just simply the location of where it crosses your y-axis. That's the coordinate 0, 1. Or you could have just said 1, right? Because we're saying y-intercept, okay, it crosses the y at 1. You could give it as a coordinate, you could give it as a number, that's fine. I think on the final they give it as a coordinate. How about the domain?
X equals all real numbers.
X equals all real numbers. Kind of like parabolas. It really does go to the left forever and it goes that way forever. But the range, this entire graph is either above or below a certain value. Y is greater than 0. Now on a parabola, it really is greater than or equal to the y value of your vertex. But right here, it's not greater than or equal to, because, ladies and gentlemen, it never actually touches the y value of 0. I mean, it looks like it touches 0 right here, but we know that it never actually touches, it just infinitely approaches. So if you put the or equal to, it would be wrong. It's just y is above 0. It's not, it never actually touches 0, so it's never actually equal to 0. Let's move on to number 28. What are the x-intercepts of the function? Well, first of all, we need to not get confused with f of x. F of x is the same thing as y, okay? Now, I have y equals 3x squared minus 5x minus 7. When they ask you to find the x-intercepts, remember x-intercepts, it means the same thing as what? The x-intercepts are the location where your parabola will cross the x-axis. And we should know that those locations, those x-intercept values are really the answer to the quadratic equation. All right? So, or how about this? How could you find the x-intercept of any equation? To find the x-intercept, what do? Set y equal to 0. To find the y-intercept, you set x equal to 0. Now, remember, I told you x-intercepts are the same thing as the roots. They're the same thing as the solutions. They're the same thing as the answers. So finding the x-intercepts is simply putting a 0 right here, or better, putting it over here, and then solving this quadratic equation. And how could we solve a quadratic equation? Using the quadratic formula. Quadratic formula is, there's the quadratic formula. In order to use this quadratic formula correctly, let's replace all the letters with parentheses. So negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a, And of course, this is x equals that. So we're going to get the actual answers, and the answers are the same things as the x-intercepts. So let's plug in. Well, let's first identify. Our a value is 3. Our b value is -5. Our c value is -7. So let's plug in the b value of -5 right in here. The b value of -5 right in here. The a value, which is what?
3.
Right there and down here. And then the c value is -7. Okay, now, whenever we work the quadratic formula, if you have a minus right here, just change it to plus. That's easy. But you always start with the discriminant value, the value inside the root. So let's begin by doing -5 squared. What's -5 squared?
25.
Okay, 25. And then what is 4 times 3? I don't even care if you include the negative or not. Just what's 4 times 3?
12.
12. And what's 12 times 7? I'm not even going to include the negative sign. 84. So is it plus 84 or is it minus 84? Now notice that there's a minus here and a minus there, and a negative times a negative ends up being a positive. So yeah, it's going to be a positive 84. Now this is our discriminant value. What is 25 plus 84? 109. So ladies and gentlemen, so far we have 5 plus or minus the square root of the discriminant, which is, let me do it in blue, 109, all divided by 2 times a, which is really 6. So is 109 a perfect square number?
No.
It's not. So I know I'm not going to get 2 nice answers. I mean, I might have to just leave it like this. But the question is, we need to look at the square root of 109 on the side and see if I could break it down to get a perfect square number with multiplication. So if I go 109 with the calculator and divide it by my first perfect square number, 4, it doesn't work. It gives me a 27.25. If I try 109 divided by maybe, it's not going to work. As I'm going through 109, dividing by perfect square numbers like 16, it doesn't work. So I believe 109 is it. You can't really break it down. So yeah, I tried with the calculator, and 109 cannot be broken down with any perfect square number. Actually, you can't even break it down with 2 or 3. You can't divide it by 2, can't divide it by 3. So you know 109 cannot be broken down. So this is your final answer. Whoa, that's ugly. That's your final answer. 5 plus or minus 109 over 6. Let's move on. Find the product, number 29. So find the product. This is a distributive property problem. We're going to take this entire monomial and we're going to distribute it. So let's first start with the coefficient -3 times 4. What's the -3 times 4? -12. -12. And then how about the r to the 4th times r to the 2nd? It is r to the 6th. Not r to the 8th, r to the 6th. Remember, when you multiply, you add exponents. And then we go -3 r to the 4th times negative. That's going to be a positive 3 times 7 is 21. And r to the 4th times r is r to the 5th. That's right. And then at the very end, we have plus 6 r to the 4th just on there. And that's it. We are done with number 29. That's it. There's nothing to combine because all of your r's are different. You have r to the 6th, r to the 5th, r to the 4th. You can't really add any of those. Let's move on. This is ridiculously easy. This is back actually first semester, right? You're distributing and then combining like terms. Now you should be very familiar with this because we did this backwards when we factored quadratic trinomials. R times r, r squared, r times -6, -6r. And then let's switch it up. Let's go 7 times r, positive 7r, and then 7 times -6, that's -42. Are you with me? And now we're just combining the middle terms, the -6r with the positive 7r. What do we get?
-1.
We get 1r. Now you don't even need the 1 really, it's just positive r. So let me bring down what I have left. I have an r squared, I have the plus 1r, I have the -42. And we're done. That's your answer for number 30. Number 31 is a problem that deals with the rules of exponents. Now remember, when you have parentheses with an exponent on the outside, you have to distribute that outside exponent to each and every exponent on the inside. So you're going to put that 3 on the 4. You're going to put the 3 right here with the 5 and with the 6. So you're going to have to actually multiply, because remember, a power to a power, you multiply. That was one of the important rules of exponents. So what we really have is 4 to the 3rd, and then we have g to the what? 15. And then we have h to the 18. And we're done. However, on the multiple choice answers on the final, they're not going to leave it as 4 to the 3rd. They're actually going to do 4 times 4, which is 16, times 4, which is 64, I believe. And that is your final answer. Moving on to number 32. Find the product. Again, really easy stuff. Multiply. That's what product means. So we're going to multiply. We're going to multiply by rewriting it first. Remember, anything to the second power means that you're going to multiply that with itself 2 times. So let's write this 7c plus 9 twice. And then from there, we need to remember to distribute one term at a time. So I'm going to start with, and I recommend sometimes to cover up a certain value if you want. And then once you distribute the 7c, then you can move that over and then distribute the 9. So if you want, you could cover them up and distribute one at a time. I'm just going to show different colors to show that I'm first distributing the 7c. 7c times 7c is 49c squared. 7c times 9 is positive 63c. And then I'm going to distribute this positive 9 right here. Positive 9 times 7c is also positive 63c. And then positive 9 times positive 9 is positive 81. So the middle terms, they could be combined because they're the same c value terms. 63c plus 63c, that's 126. So my final answer is 49c squared plus 126c plus 81. 49c squared plus 126c plus 81. And I think I'm going to end it right. Should I end it or just do one more? One more. Why not? One more. Okay. So number 33. 33. We have a polynomial or plus a polynomial. Now, if it were multiplied, you'd have to distribute and then combine like terms, but it's plus, so all you have to do is just combine like terms. So you're going to start with the highest exponent term and alphabetically, all right? So this is kind of confusing because, first of all, you don't just have a's, you have a's, b squares, and a's. Then right here you have b, you have a 9 and an a squared. So according to number 33 here, let's look at the inside of this parenthesis first. Is there anything I could combine? Yes. If I just look at the inside of this parenthesis?
7a and negative 3a.
And what do we get?
4a.
We get 4a. So 7a combined with negative 3a, we get this 4a. Let me bring down the minus 2b squared. And then let me look at the other parentheses. Is there anything to do? Oh. There's nothing to do over here. Okay. So let me just rewrite everything. So let me put the plus b minus 9 plus 13a squared. So I have this ginormous expression without parentheses now. By the way, this plus sign, it doesn't change any of these terms. So that's why I could just rewrite it without parentheses. The b's right there, the minus 9's right there, the 13a squared's right there. And now we need to combine like terms. Let's start with the highest exponent, and let's start with the first term alphabetically, which would be a squared. So the first part of our answer will be 13a squared. And then we go for the next highest exponent, and it's still the square, but this time we have b's involved, so it's going to be minus 2b squared. And then we go to, we already did the squares, let's go down to the regular letters. We have a positive 4a, that's next. Right here we have a positive 4a, let's bring that down, plus 4a. Do we have any b's up there? Yes. Yes, we have one positive b right there, so let's write that next, positive b. And the only thing left is the constant value, the negative 9. So let's bring down that negative 9. And now we are really completely done. There's nothing else to do. So that's your final answer right there. We'll pick up the rest of this on the next video.